Okay, so what we're going to look at today are the parent function transformation notes. So this is where knowing your parent functions comes in handy. It's really, really important. And so on your Canvas, if you go to the 1.4, you can open up your own Google Slides and fill in the notes while you watch the video, or you can just look here, or you can just look at the key. So that second slide is a video. I'm not sure if I can play it while I'm recording my screen. But if you want to watch it, it's just a really quirky, funny, silly video that really doesn't have to do with transformations, but it does talk about how Thor in the beginning, when he is a super fit god or whatever, and then by the last Avengers game movie, when everybody leaves or disappears, he gets depressed and fat and sad and, got that beer gut going on. So it's just like a really quirky little video if you want to watch that. If not, don't worry about it. If we look at slide 3, we are given some information. We're given some things about the graph. We're given some things about the functions. And so if you'll look here, we see that the original function is x squared, and then the function transformed is f of x plus 3. So that's the same thing as saying x squared plus 3. And if you start with the parent function here on the left, a regular parabola, and then the parent function here on the right, it shifts up 3. And so the description of the transformation will say vertically translated up 3 units. And so that doesn't change the domain. So I've got this little infinity sign there. You can copy and paste. So the domain is negative infinity to positive infinity, and your range changes from 0 to infinity to 3 to infinity. And that's all the information we can say about that. So if we look at slide 4, that's an absolute value function. And so my transformed function is f of x minus 5. If we look at the graph, we see that minus 5 vertically translates it down 5 units. And so then that also does not change your domain. So it's negative infinity to positive infinity, but it does change your range. So your range goes from 0 to infinity from to negative 5 to infinity. Remember, range is bottom to top, range is left to, domain is left to right. So then, if we look at the next one, we've got a cubic function, so x cubed, and so my function notation is f of x minus 4. So that minus 4 is now inside the parentheses. It's directly affecting the x. And so the description of this transformation, if you'll look at your graph, the origin, the point that crosses the origin is now on the right, so it crosses at 4. So we can say horizontally translated 4 units to the right. And so my domain for cubic functions, it's really funny because your domain and range very rarely change from negative infinity to positive infinity. They're pretty much always that. All right, and then in slide 6, we've got a square root function. And so what we see is we've got a plus 5 inside the parentheses with our function, and we see that the point from the origin moves 5 to the left. And so this one is horizontally translated 5 units left. And so if you'll notice, when you're going left and right, it's opposite of what you think. So when we have a plus 5, we're going to the left, but when we have a minus, we're going to the right. And so this domain changes. Horizontal shift, so horizontal is left and right. That will affect your domain, but it does not affect your range. So my domain is now negative 5 to infinity, and my range is 0 to infinity. If we look at slide 7, we have a cube root function, and it functions similarly to the cubic, where their domain and range rarely change from negative infinity to positive infinity. But we do see that we have some shifts from the original parent graph. So it looks like we go down some and over some. So we go down 4 and left 3. So we've got a vertical translation down 4 and a horizontal translation left 3. And so order doesn't necessarily matter when you're doing those, not when you graph it and not when you are stating it. And so your range actually doesn't change. If we look at number 8, we have got our original function x squared. That's a quadratic. It creates a parabola. And the equation of the transformed function is a negative f of x. And so what that does, if you look at your graph, it flips it over the x-axis. So mathematically, we say reflection over the x-axis. That doesn't affect the domain, typically, but it does affect the range. So x-axis is the horizontal axis, but when you flip it over, you're actually making a vertical movement, and so that's why it affects the range and not the domain. So my range is now negative infinity to 0. All right, slide 9, we've got a square root function again, and my function is f of negative x. So that negative is affecting my domain, not my domain. It's affecting my x directly. And so the description of the transformation, if you'll notice, is a reflection over the y-axis. So up until this point, all of the other transformations should be reviewed. This one might be new. And so it's only a little bit challenging because you've got to remember where the negative goes. So if it's in front of the entire function, it's over the x-axis. If it is just with the x, it's a reflection over the y-axis. All right, and since it is a horizontal reflection because it's moving horizontally, our domain is what's going to change and not the range. So my domain here is going to be negative infinity to 0, and my range is just like the parent function, so 0 to infinity. All right, slide 10, we've got another absolute value function. We see that in the parent function, it opens pretty wide, but in the transformed function, it is opening a little bit smaller. So we see that that is a vertical stretch. So imagine that you're pulling the top of the function to the bottom of the function, and you've got a stretch. So you're making it taller and skinnier. And so since we've got a function 3 of f of x, we're going to say a vertical stretch by a factor of 3. And so stretches do not affect your domain and range, so this is where knowing your information comes in handy. And so if you're studying that reference sheet, that should help you out. All right, slide 11, we've got a quadratic function, we've got a parabola, and you'll notice that the opening is wider. So here we've got a vertical compression. And so that is where, if you'll imagine, pressing on it from the top and the bottom, and so you're making it flatter. And so vertical compression by factor of 1/2. And you'll have to get the factor, unless you're going to work it out, you'll have to get that factor by the equation. And so again, your compression does not affect your domain or range. So it should mimic the same as your parent function. 0 to infinity. All right, slide 12, we've got a cubic function again. And so this one is kind of tricky to see, especially because your graphs aren't exactly the same. But what you see is that it should get a little bit skinnier, so that span where it starts shifting from increasing to decreasing, that turnaround spot is a little bit smaller. And so here we actually have, graphically, it looks just like a vertical stretch. But according to our function, it's not. So this 2, instead of being in front of the entire function, is inside with the x. And so it's a whole number. And so we actually know that it's going to be a horizontal compression by a factor of 2. And so if you're thinking about it, horizontally compressing would be pressing on that graph from the left and to the right, and so you're making it taller and skinnier because you're pressing it from the outside. on the left and from the right. And so a horizontal compression and a vertical stretch do the same thing graphically, but they show up different in your function. And so horizontal compression, horizontal stretch doesn't affect your domain and range either. So it'll match the exact same as your parent function. All right, last new one, we've got square root of x. And so again, it's a little bit trickier to see on this graph because they are different. But we see that we've got a 1/3 in with our x inside those parentheses. And so here we've got a horizontal stretch. And so that would be pulling apart the left and the right, and you're stretching it and you're making it flatter by a factor of 1/3. And so again, it doesn't affect your domain and range from your original parent function. So your domain is 0 to infinity, and your range is actually the same as the domain. All right, so putting it all together, slide 14, we are only given the transformed graph. And so it's got that point, and so we can already say that the parent function is the absolute value. So I'm going to go up here to slide 4 and copy and paste my parent function, just so we kind of have a side-by-side view. And so my parent function is absolute value of x. That's the equation. And if we compare the openings, the parent function opens up, the transform function opens down, so we know we've got a reflection over the x-axis. We also can compare the vertex and see that the vertex originally is at the origin and my new vertex is at 2, 3. So we know that it has been horizontally translated to the right 2 units, and we know that it's been translated up 3 units. As long as you know the mathematical terminology every single time, I don't care if you write it out, as long as if I give you a multiple choice exam and you've got multiple choice answers, you know the difference between vertical and horizontal and all that stuff. So for the transformed function, we've got to have all that information in there. And so we're going to actually write it 2 ways. So reflection, we've got a negative in front. Left and right is inside our parentheses or absolute value brackets. And so if we go to the right, we subtract. And if we're going up, we add 3. So I'm going to add some spaces in there so you can see all those. Make it a little bit smaller so it fits. All right, and then the second way that we can write it is just using the f of x. So if we have defined f of x as the absolute value of x, what we can do is say negative f of x minus 2 plus 3, as long as f of x has already been defined. And so a reflection over the x-axis, right 2 and up 3, doesn't affect your domain. Oops, I didn't have it copied and pasted anymore. All right. But it does affect your range because we have shifted it up off of that axis. And so my new range is going to be from negative infinity all the way up to 3. And so the domain and range is really the trickiest part, to be completely honest, in my opinion. And so just be really careful with that. Domain and range, domain is left to right, range is bottom to top. All right, so slide 15 is a little bit tricky, so I'm going to go ahead and copy my parent function from slide 11. All right, and we see a couple of things. We see that my vertex has shifted down from 0, 0 to 0, negative 3, and that my x-intercepts are now negative 1 and 1. And so from the graph, it's really tricky to see, but it actually has been vertically stretched. And so to figure out that stretch factor, you're going to have to compare some points and you're going to have to figure out your A value. So it's too challenging to write all of that out on in this video on my screen. So if you'll remind me in class, we can do it together in person. And so we can practice a couple of those. But I'm going to fill out the general stuff, but I'm not going to work out to find our transformed function just yet. So we know that it is x squared. We know that it has been vertically stretched, and we also know that it has been vertically translated down 3 units. We're going to skip the transform function because we don't know that stretch factor, and then my domain is negative infinity to positive infinity. And like I said, if you'll remind me in class, I will work out how to find that stretch factor. You basically just start with your parent function in vertex form. So you would start with your y equals a times x minus h squared plus k, and then see if you can solve for a. So you would plug in an x and y value, you would plug in your vertex value, and then you would solve for a. So it's not that difficult, but I just don't have the capability to show you that on my screen at the moment. So let's see. All right, slide 16, almost done. I think we got 3 left. We've got a square root function, and so we are given the domain and the range. So that domain, if you think about a regular parent function for a square root, the domain is from 0 to infinity. So it ends by going all the way positive. But in this case, we are starting in the negative region and ending at 3, so it doesn't go on forever in the positive direction. So the only transformation that could account for that is a reflection over the y-axis. So it flips it over. And then if my range, and it stops at 3. So if I just reflect it over the y-axis, then my highest x value is a 0, but I need it to be 3. So that means that I'm translating the function to the right 3. And then if my range is 2 to infinity, I know that it has been translated up 2, because originally we start at 0. And so my equation of the transformed function will be, I'm going to copy and paste the square root over here. The negative needs to be inside with the x because it's over the x-axis, y-axis, I'm sorry. And so if we go to the right, we subtract, and if we go up, that's outside of your square root function. And so I'm not going to graph that one, but you could very easily go to Desmos and graph it. I'm not going to graph it and move it to my picture. But we did say the square root of x, negative x minus 3, plus 2. So it's a good thing that we checked because we aren't taking into account this negative in the front. And so technically, if we factor it out, we're adding 3 to move it to the right because of that -1 of affecting that x value. So good thing that we checked. Let's make sure everything else is right. The domain is negative infinity to positive 3, range is 2 to infinity, so it looks like we have our answer. So change that. All right, slide 17. All we are given is the transformed function, so we can jump right into our transformation. So we've got a reflection over the x-axis. We've got right 2 units, and we've got down 4 units. And so it's a cubic function. You've got that cubed in there. Oh, hello. Let's go ahead. Superscript first. All right, and cubic functions, it doesn't matter which way you move it, the domain and range are always the same. So those are always really nice and easy for domain and range. You don't really have to think about it. And so you can go ahead and click and drag your parent function if you want to. And then last one before we sum it all up. So we are given a cube root function that has been translated right 3 units and up 4. So let me see if I can find my cube root function. I got an extra symbol in there. All right, cube root of x. So it's the inverse of a cubic function. And its transformed function, if it's been to the right 3, we'll subtract 3. And if we go up 4, we add 4. And so your domain for a cube root function is the same as the parent function. And so it's all real numbers, negative infinity to positive infinity. And so you can always click and drag your parent function graph. So to sum it all up, if you're going to write anything on paper out of this entire lesson, it would be these last 2 slides, just because it lists out all of your transformations for you. So if you have a function and outside the function you add c, you are vertically translated up c units. If it's minus c, you are vertically translated down c units. If it is inside the parentheses, you've got horizontal movement, so you've got a horizontal translation. Left c units when it's addition, and right when it is subtraction. Let me make sure I spell all those right. If there's a negative in front of the entire function, it's a reflection over the x-axis. And if it's with your x, it's a reflection over the y-axis. So that one is one that is really difficult to see, just the difference when you've got your function. And so just make sure if you are confused, just to graph it and check just like we did. All right, this list right here is the list for rigid transformations. And what I mean by that is that rigid transformations are just moving your function to a different location. So left, right, up, down, doesn't change the shape, doesn't change the opening, it doesn't really change it other than where it's located on your graph. So your non-rigid transformations are actually affecting the shape of it. So those are your stretches and compressions. And so this is the same thing. With your function, your names are different, but with the graph, you can call it either horizontal stretch and vertical compression. Those are the same, or you can say a vertical compression and a horizontal stretch. I think I said those right. And so if you've got a whole number in front of your function, you've got a vertical stretch. If you have a fraction, you've got a vertical compression. If your whole number is inside with the x, inside those parentheses, inside the function, you've got a horizontal compression. And you've got a fraction inside, you've got a horizontal stretch. And so I'm going to highlight these so that you know which ones do the same thing to the graph. And you can think about pressing on a ball. So a vertical stretch and a horizontal compression are the same. And then your vertical compression and your horizontal stretch do the same to the graph. Let me highlight. And there you go. So once you have filled this out on your Canvas, if you'll submit it, it's a free 100 participation grade. And then you can work on your homework. Email me if you've got any questions about any of it.